Okay, so good afternoon and good morning, friends. So it is a great pleasure to have Dr. Ali Övgün with us. Dr. Ali Övgün from the Physics Department of Eastern Mediterranean University. So, Dr. Övgün, the stage is yours. And already you share the screen. Please start it.
Okay, good afternoon, everyone, and thank you very much for your invitation. Today, I will talk about testing the modified gravity through the black hole shadows and also deflection of light. Let me first give a brief roadmap of talk. I will begin with a short introduction, especially for students, and explain what a black hole shadow is and why it is not same as the event horizon. Then I will summarize some of the most important developments from Event Horizon Telescope observations. Finally, I will focus on recent work where we developed generalization perturbative framework for gravitational shadow and show how energy-dependent shadows can have uh, distinguish different geometric deformations. So, general relativity has been extremely successful. It explained the classical test of gravity, binary pulses, gravitational waves, and even horizon scale black hole observation remarkably well. However, there are also still deep open questions, including dark matter, dark energy, space-time singularities, and quantum gravity. So the issue is not the general relativity has failed. Rather, the point is that strong gravity observations now allow us to test whether general relativity is the complete description of gravity or we need some modification or alternative theories. So let me begin with the basic definition of a black hole. So classically, black hole is a region of space-time where gravity is so strong that nothing, even light, can escape. And as John Wheeler said that general relativity in two sentences must tell space how to curve and space-time tell mass how to move. And the event horizon is as I said, that is the boundary of no returns. And in the standard picture, the central region contains also a singularity where curvature become extremely large. So in this simplest description, we can say that black holes are characterized by only three important uh, things: mass, charge, and angular momentum. And we are lucky that we observe the black holes directly, firstly with the LIGO by the gravitational waves, and after that with the Event Horizon Telescope collaboration, and after 100 years of Eddington Dyson solar eclipse observations. So this Event Horizon Telescope is a very large telescope array and consisting of a global network of radio telescope. And in 2019, the Event Horizon Telescope Corporation published the first image of a black hole in the nearby galaxy M87. And this is a very huge step. And this telescope has an antenna, and each antenna spread out over vast distances, and has an extremely precise atomic clock. So analogy signals collected by this antenna and then converted to digital signals and stored on hard drives. And these hard drives are, I think, from Earth to the Moon. So there are many information stored there, and they all after that study these informations and find this black hole shadow image. And Event Horizon Telescope is a global array of a radio telescope and operating together through a very long baseline interferometer. And as I said that by combining data from telescope spread across the Earth, it effectively creates an Earth-sized telescope. And each station records the incoming signal with extremely accurate atomic clocks. And then the data are later combined to reconstruct this image. This is how horizon scale imaging of black hole become possible for us. But before observations done, Luminet and then Falke successfully predict the shape of the shadow, and the Luminet did it in 1979, and after that, Falke did it in 2000. And the key point is that the black hole shadow not is not the event horizon itself. The shadow is the dark region on the observer sky, which is produced by light rays that are captured by compact object. And together with the strong lensing around this object, around the unstable photon orbits, so that the shadow is an observable consequence, you can say it, of space-time geometry. So its size and also shape encode the information about the metric near the compact object. And here, this slide gives a very good visual intuition for that idea. What we observe is not the black hole directly, but rather the effect that gravity has on surrounding light. And this dark region is a shadow, while the bright structure around it comes from lens emission. This is why this shadow image is such powerful probe of strong gravity. Firstly, Event Horizon Telescope observed M87, after that Sagittarius A in 2022, and lastly, they use the artificial intelligence and improve the figure. So in real image, the photon ring and the surrounding emission from accretion flow or jets are not perfectly separated. So when we analyze observed black hole image, we must remember that the shadow boundary is inferred through a complexity of geometry. Also, there are some astrophysical emission and also instrumental resolution. And this shadow boundary is determined by critical trajectories. So if this light ray passes far enough away, it's only weakly deflected. So if it is passed too close, it gets trapped or falls inward. And the boundary between this escape and capture is controlled by unstable circular or near circular null orbits. And often we say that these are photon sphere in static spherical case. This is why this deflection of light and black hole shadow are deeply connected, and both are probes the same geometry. Yes, even though black holes are invisible, their influence on light can reveal their presence and properties to us. And isn't it amazing how nature used the light and gravity to create such extraordinary phenomena? And you can see that some regions are bright and some regions are red because of, as you know, that the radiation from gas and dust moving toward us appear brighter. On the other hand, the other side, radiation from particles moving away appear dimmer, and this imbalance makes the ring appear brighter on one side. So while we primarily look at the Sagittarius A and M87, because Sagittarius A and M87 are the two best supermassive black hole candidate for horizon scale imaging. The reason is the plot compares source brightness and angular resolution here. As we move toward higher resolution, these two sources stand out as the most favorable laboratories for strong gravity studies. In particular, this Sagittarius A is the closest observable supermassive black hole, which is located center of our galaxy. And on the other hand, M87 is also extremely massive, which is also make its shadow large on the sky, so that we focus on these two black holes. So there are one important way to improve the Event Horizon Telescope is to increase the sensitivity and also the angular resolution. This can be done by observing a shorter wavelength and increasing the collecting area and expanding the baseline network. And since angular resolution scales roughly like wavelength divided by baseline, short wavelength and larger baselines also allow us to resolve the finer structures. And this is very essential for improving the shadow measurement and testing gravity more precisely. So in the future, we expect to add 345 gigahertz as an observed frequency in the near future. So if you look at the theory part, study of black hole shadow has a long theoretical history. Firstly, Singh already in 1966 calculated what we will now call the shadow of a Schwarzschild black hole and find the photon sphere preamp. Later, Bardeen gave the correct shadow construction for the Kerr black hole, where rotation makes the shadow asymmetric. Since then, many studies have generalized the shadow concept to a wide variety of black hole and compact object spacetime. So why are we interested in gravity beyond Einstein? Because even though general relativity works extremely well, there remain major unresolved problems, as I said before: dark matter, dark energy, Hubble tension, singularities, and also challenge of recalling gravity with quantum theory. And observation of black holes now give us direct way to test gravity in the strongest accessible region. And this is exactly where small deviation from standard picture might become visible. And this very long baseline interferometer is the technique that makes all of this possible in radio astronomy, and it allows us also signal from distance telescope to be combined coherently and also achieving extremely high angular resolution. And without this VLBI, horizon scalar black hole imaging will not be possible. So if the observations are sufficiently accurate later in future, it can be provide us the evidence of existence of shape of the horizon, maybe testing Mohr theorem GR, and maybe testing GR itself against a number of alternative theory gravity. Also, there are many possible alternatives to the standard black hole picture. This includes spacetime with additional charge, higher curvature effect, or horizonless compact objects such as Gravastar. So the important point is that the shadow observation may help distinguishing black holes from black hole mimickers, at least in principle, by comparing the prediction image and structure with observed data. So this is also another important point. So now let us move toward the mathematical distribution. So the shadow boundary is determined by critical light trajectories in the black hole spacetime. So if you consider the static spherical symmetric line element in this form, and if you say that motion is confined to equatorial plane, then the problem reduces the understanding null geodesic and identify the unstable circular or near circular orbit that separate capture from escape. So after that, this problem will be very similar to the one-dimensional classical mechanic, where the radial motion is governed by effective potential. A very important quantity is the critical impact parameter, which separates photons that escape from those that are captured, and the critical value is associated with an unstable circular light orbit or photon sphere in static spherical case. And by solving this condition for a circular orbit and its instability, we calculate the radius of the photon sphere and corresponding shadow size. And if you look at the figure, this figure gives the intensity meaning of the critical impact parameter. If the impact parameter is very small, the photons fall into the black hole. If it's large, the photon escape to infinity. At the very exactly the critical value, the photons asymptotically spiral around the unstable circular orbit. And in the Schwarzschild spacetime, this corresponding to the photon sphere, while if you go to the rotating spacetime, like a Kerr spacetime, the structure become more complicated and form photon regions rather than a simple sphere. So, for example, for the Schwarzschild case, the photon sphere is located at 3 amp, and you can calculate the critical impact parameter, which is the shadow radius, is 3 root 3 m. So in general, the size and shape of the shadow depend on several factors. They depend on black hole parameters such as mass, spin, and possible extra charges. They also depend on observer position and inclination angle, and also on the medium through which light propagates, for example, plasma. So we can say that the shadow is not just a property of a black hole alone. It is also a result of geometry, which is propagation and observation. So generally speaking, we can say that the size and shape of the shadow depend on parameter of the black hole, like a spin A. Here you can see that the shadow becomes deformed if the black hole is rotating, and this is very easy to observe it. So if the spin parameter is increased too much, the deformation is increased. But from the observation, we know that the black hole spin should be very small, so that we can say that curved black hole shadow depends only weakly on a spin. So here there are some figures, I will show it here. You can see that by using the recent observational data from the Event Horizon Telescope, this result cannot place constraint on the parameter in the curve metric because radius must be between 4.31 m and 6.08 m, which gives us 70% constraint. So we can say that this is very weak. So here you can see that from the observation point, spin parameter should be very small, so that it is very difficult to use it as a constraint. So as a conclusion, they find no noticeable difference for curve and line curve images. If you look at the Sagittarius A observation, that time they give 10% constraint for the spin parameter. Okay, so what we did, so I first started to work on the shadow of the black hole in 2018 by this Jacob paper. So firstly, we studied the shadow cast and deflection angle of Kerr-Newman Causal spacetime, which is a dynamic black hole, rotating black hole with magnetic and electric charge together. And for a fixed spin parameter, introducing an additional magnetic charge can reduce the shadow size relative to the Kerr case and also increase the distortion. At the same time, we show that both shadow observable and lensing observables respond to the same geometric deformation. After that, there are many studies, and these authors work on the constraint of black hole charge. And they said the black hole shadow size depends on black hole physical charge, and they use the Event Horizon Telescope data to constrain the different charged black holes and regular black holes. Once we have observed the shadow size, we can use it to constrain many parameters. In the sense that here they show that how the charge affect the black hole shadow. In the most cases, yes, when the charge is increasing, shadow size is decreasing, but in some cases, it behaves differently. Yes, as we can say that as a common trend is that extra physical charge often change the shadow radius, although behavior is not always universal. Some regular black hole solutions remain compatible with present observation, while other highly charged solutions can already be disfavored by Event Horizon Telescope. And by using after that Sagittarius A observations, they make a 10% bound can place constraint on part of the parameter space for metric that deviate from Kerr space-time. So by inspiring these papers, we also scan more than 50 different black hole spacetimes using the Sagittarius age data and find some constraint to different parameters. This topic has attracted a great deal of attention, as reflected by the large number of citations, more than 900 citations in 2.5 years. The reason is, of course, simple. Black hole shadow now sit at the intersection of general relativity, modified gravity, astrophysics, and also observational astronomy. So there are many people working on this topic. Also, recently, we developed a new analytic approximation model with my visitor, Vitaly Vertekurado. And later that, by Kobyalko and Kastov developed this approach, perturbative approach for gravitational shadow in static spherical symmetric spacetime. And basically, our goal was to relate deviations of metric directly to deviation of the shadow radius. And this provides a very useful foundation for more general shadow spectroscopy framework. And after that, expansion of the gravitational shadow radius in terms of these parameters are constructed up to the second order. The metric expansion also in terms of Schwarzschild mass to radius ratio is the reconstruction. And we find explicit analytical expression, and we use it for different examples. And in some cases, perturbative result may also demonstrate good accuracy, even for non-small deviations. For example, this is one of the black hole solution. And when we calculate, by using this method, we can calculate the photon sphere and also shadow radius easily. Especially this method is very good if the Laps function is very complicated and it is not very easy to find direct analytic method. That's time it is good to use this perturbative method to find approximate solutions. So later, this end of this year, we also improve this method with my collaborator Reggie Pantic and publish in Physical Review. And we use that the massive shadow spectroscopy, which turn the shadow into an energy result probe. Instead of one chromatic shadow, we obtain a family of shadows that depend on the particle energy. And also this gives us a way to separate temporal and spatial metric deformation that would all otherwise remain degenerate in ordinary photon shadow analysis. So basically what we did, a complementary direction is to go beyond the massless probe. We use the massive test particle and also admit energy dependent massive shadow. And building on this idea, basically we follow the idea of Vertekurado and my paper before, which we generalize analytic approach that contact deformation to metric and photon sphere and shadow. And after that, we also use the idea of Kobyalko, and we calculated this time and generalize it to the up to the third order, because the Kobyalko did it for up to the second order. We generalize it to the up to the third order. Basically, how we did it? Our formalism, first we start from the most general static spherical symmetric metric, and we expand all metric function, not just this temporal one. The crucial generalization is that we don't fix the areal radius function to its standard form. Normally, you can take it R squared, but we take it as a approximation. So that means that deformation of the spatial sector are included on the same footing as temporal deformation. We then solve perturbatively for the massive particle, sphere radius, and correspondingly find observable shadow radius. So this left side, you can see the first order. what Kobayalko and his collaborator did it, and after that we extended for the second order. And in the second order, there are also more nonlinear coupling theorems. Of course, while the first order expansion revealed the linear response of the shadow perturbation, it is often insufficient to distinguish between different alternative theory of gravity, as distinct physical model may be constructed to yield identical first order shadow. To break this degeneracy and probe the nonlinear structure of these theories, we must extend our analysis to the second order in the perturbative parameter delta, so that we did it in this paper, and we found very good result. This is the main conceptual result of that paper. As the particle energy changes, the unperturbated orbit radius move from the photon sphere scale nearly 3 times the mass toward to the 4 times the mass in the non-relativistic limit. So here you can see the radius versus epsilon parameter. In the sense that one shot
F206 kilometer.
Here the figures show how predicted shadow observable respond quantitatively to the perturbative parameter. So that we can say that the broader interpretation is that shadow spectroscopy provides more information than a single black hole image. It can at least in principle help disentangle which part of the network is being modified and where those modifications are most relevant. If you look at the future experiment, we can see that the next generation Event Horizon telescope is planned to constructed. This higher resolution image can be achieved by going to shorter wavelength and adding telescope, and also ultimately doing interferometer with space instrument. And this next generation Event telescope will add 10 more telescopes, including observing at 86, 230, and 345 GHz, and improve also angular resolution by 10 times. And this will enable more movies of M87 and also Sagittarius A, and also capture the photon rings. And also placing telescope in Earth orbit eliminate atmospheric effect that distort and blur ground-based observations. There are also they also develop different missions. Concept of Black Hole Explorer since 2019, and will propose it as a NASA Small Explorer mission in 2025. But after that, they plan to launch it in 2031. This will achieve the highest angular resolution in history and will reveal a black hole photon ring for the first time. And also, they plan to first direct measurement of a black hole spin. Then also opportunity to study dozens of black holes, leverage millions of dollars of grant in France ratio, and also exploration of community interest in photon ring. And if you compare with the Event Horizon telescope, you can see that approximately 36 times sensitive and multiband, because the data are very huge, 96 gigabytes per second. And this black hole explorer with France speed 750 times more data than radio astronomy. And you can see the project. This is the lifetime will be 2 years, and orbit is 25,000 kilometers altitude. And there are many good universities who are contributing to this project. I hope that we will see. And also on the gravitational lensing part, recently also we have developed some new methods. Firstly, in our earlier work with Lee and Zhang, we introduced a geometric framework based on the Jacobi metric to study circular orbit and with gravitational lensing in static spherical symmetric spacetime. We apply this framework to both null and time-like particles and use Gauss-Bonnet theorem to derive deflection angle. An important feature is that this approach can also be extended to the asymptotically non-flat spacetime. So this is what we do after extending the Gibbs and Werner method and extend the Sierra et al. Method. And recently also with Regiquantic we have in our more recent work, this one, we extend the finite distance Jacobi metric using the Gauss-Bonnet framework to spinning massive particle. And this is also recently published in Annals of Physics. At a dipole order, the Mathison-Papapetrou-Dixon dynamic generally drive the trajectory away from the ordinary Jacobi geodesic, so that the standard Gauss-Bonnet construction must be reformulated. And working in the aligned spin planar sector and keeping terms like linear in spin, we derive a spin generalized deflection, which identify in which the spin dependence enter. Here you can see S. An additional boundary function involve the geodesic curvature of physical ray. We then apply this framework to some example like Schweitzer-Grazer-Nordstrom and also Kotler's geometry and calculate the deflection angle. You can see that leading spin correction is linear as enter to be deflection angle and how spin parameter effective. So as a summary, we have detected shadow of the black hole for the first time, and its size and shape are broadly consistent with the prediction of Kerr break. And these observations also allow us to constrain different charges and deviation from standard black hole picture. And more generally, horizon scale image of supermassive black hole have opened an entirely new window onto gravity and fundamental physics in strong pit region. We can say that the future also looks very promising. So additional telescope maybe will improve the image fidelity and may also allow us to measure shadow asymmetry more accurately. And the first image of M87 already allow a significant constraint on the shadow radius, and Sagittarius A also provide another powerful target and constraint. As observational uncertainties decrease, this measurement also later can be used to constrain modified gravity black hole and more strongly. So we can say that the future of black hole shadow test is indeed very bright. So I suggest to young students, young researchers to jump on this area and study. Here you can see also another black hole shadow picture. Black holes are surrounded by plasma, and this plasma also contains magnetic field. So as the magnetic field becomes stronger, it changes the structure of the flow, also the pattern of polarized light. So this polarimetric observation of M87 indicate the also presence of strong magnetic field near the black hole. And this magnetic field also may be play an important role in the orbital dynamic and in the formation of jet, which remain one of the major questions in also modern astrophysics. So thank you very much for your attention. I will be very happy to also take your questions. Thank you very much.
Thank you. So
Thank you.
let us go for the discussion. So Devasmita, you can go ahead.
Yeah, hello, sir. It's a excellent talk. Sir, actually, I have doubt in that shadows of black hole. Actually, like black hole has event horizon. Now I'm working in Gravastar, but in Gravastar there is no event horizon and singularity in the interior region. So what is the since Gravastar has no event horizon, so when the impact parameter is small, the photon energy. So, like in black hole, since the black hole has event horizon, so when the energy of photons is much more greater than the effective energy of photon sphere, that time in black holes they create the like black hole shadows. So what type of things happen in Gravastar case? Since Gravastar has no event horizon.
Um, yes, I, as I understand, you ask about the Gravastar. For Gravastar, yes, there is no horizon. So Gravastar are not a black hole. So they are very different than the black holes. There are some papers related to the shadow of the Gravastar also. But I think that if you look at the recent observations and papers, the Gravastars are also excluded from observation. So I think that there is no Gravastar in the nature. Yes, any question?
Sir,
Yeah.
my question is it when the impact parameter is less than that critical impact parameter, that time is there in any changes in that photon ring in that interior region?
Sorry, but I didn't understand. If you write me on the chat, maybe I can help.
Okay, sir. Thank you,
Okay,
sir.
thank you.
Yeah, Saindan, you can go ahead.
Yeah.
Okay, sir, thank you for very excellent talk. So I'm just asking that what you have given in the last part where you have used probably the Gauss-Bonnet one. So how is it very different from say the Gibbons and say Petrakuna's work? I mean, is it like in the strong lens limit all of the three converges, or I mean, is it little bit different? Because I think Petrokuna probably has a code regarding also that. I mean, for card one, how to use the topological arguments to get that. So I was just trying to understand. In the next
Yes.
slide.
Yes. Okay. Thank you very much. Here, basically, we use the Mathison-Papert-Dixon dynamics for spinning particles, and after that, apply the Gauss-Bonnet theorem. So this is different than the null geodesics. I suggest you check our paper, and also there are some reference paper which use this Mathison-Papert-Dixon dynamics, and this is nowadays very hot topic, spinning particles. So they are a bit different than the null geodesics.
So those are all in strong lens, right? Strong lens limit.
Here, no. Here we did it for the weak deflection angle, not very strong limit.
But the impact parameter, when you get the geodesics one in the previous, it seems like a strong. Okay, maybe I'll check. And the second question is little bit of for the data when you were saying, is there any repository or like GitHub to at least check for the synthetic data? Because if I understand correctly, when you are drawing the card metric shadow, you are using the celestial coordinates, right? Alpha, beta, what Chandrasekhar defined, right? I mean the celestial alpha, beta angle and getting the circle. But when the radio astronomer, say event horizon, etc., gets a feedback of the radio dynamics, right? So I'm just asking that how this data matching has been done, like because
You
alpha
mean
beta
here?
those angles are the
No,
celestial.
no,
Yeah.
no. Here the alpha beta is the metric GTT and GRR, and also the theta part, not about this terrestrial one. So they are like metric functions.
I see. So
Yeah.
when one takes the data and put it into the celestial coordinate, when you draw the circle, that deformed circle for the car one, so how does one matches the data with this celestial coordinate? Like what is the mapping that is used?
Yes, I think we didn't check it. So we only look at the shadow radius at the infinity. So it's a good question. Maybe yes, one should check it.
Sure. Okay, thank you very much.
Thank you.
Yeah, Farooq sir.
Oh,
Yeah.
hello. Ali, how are you?
Hello, Professor. Fine. And you?
So good. So very good lecture. So why we're not interested on the Einstein cavity? Why we use the modified cavity? My concern about still, uh, I am very much concerned about modified cavity, but still I am rely on Einstein cavity.
Yes.
So what is your perspective? Also, Professor Shao also.
Yes, I think Einstein gravity is very well tested, so no need to another gravity theory. But unfortunately, we don't understand what is dark matter, dark energy, and so that we need something more. So to explain these kinds of problems, we need some modified gravity theory. So I'm not sure if the Einstein gravity is valid for all energy level. For example, if you go to the Big Bang or at the inflation area, maybe we need some modification. If you go to another planet area, okay, Newtonian gravities work well. So I think that different energy level, maybe we need different gravity theory.
But for astrophysical aspect, you can rely on Einstein gravity. I think
Yes.
as per I
Yes.
believe. But cosmological
Yes.
sense, okay, you should consider the modified gravity, otherwise unless you can. So for astrophysical objects, I think one should march attention on Einstein gravity.
Yes. Also, if you
So
go to the
Professor
black
South
hole.
also. So
Also, Einstein gravity is not enough to explain interior of black hole and at the singularity point. So to find maybe quantum gravity, it's not possible. So we need also new theory or new modification.
okay, well, I understand all. Okay, good. Okay, fine.
Thank you very much. A good question.
Yeah, Ali, so there is a chart, you can go through it.
Okay. Okay. Yes, I have worked on the shadow of the Grava star before. So yes, Grava star has no event horizon, but you can define some region. You can for the black hole shadow, the event horizon is not very important. Important is of course photon sphere. And first you want to calculate photon sphere, and after that you can calculate the shadow radius. So that in theoretically, yes, you can do it. You can calculate the shadow radius, but if there is no event horizon, yes, this photon not captured by Gravasta. But I think these are similar to the also wormholes. If you calculate the shadow of the wormhole, also wormhole has no event horizon, so they have only some mount or throat. So if the photon fall inside this throat, it can pass to the another region of the space-time. So I think this is not a problem for calculating shadow. But yes, the image of the shadow will be of course different, not very black, maybe. Okay. I think it's not same like a black hole. The images will be different.
Okay, so if there is no more questions, then let us thank the